This is a video looking at the electromagnetic spectrum. Okay, EMS for short. EMS. Okay, before I talk about this idea of the electromagnetic spectrum, I want to talk about what motivated the search for different types of radiation. So it all began in around the 1860s. So in 1865, this brilliant mathematical physicist named James Clerk Maxwell came up with a set of equations which described light. So what Maxwell did was he had 4 equations on how electricity and magnetism work. He had 4 equations. And when he manipulated these equations, using some calculus, he came up with something amazing. Came up with a number. These 2 quantities here, so mu naught and epsilon naught, these are just numbers, okay? These were known at the time from experiments. When he plugged in these 2 numbers and 1 divided by these and took the division with 1, took the square root, he found this number pop out, roughly 300 million meters per second. In other words, electricity and magnetism, when they change into each other, they do so at the speed of light. So let's say an electric field. So let's say you've got, for example, an electron, a charged particle moving along. A fact of classical physics is that whenever you have a charge moving along a wire, let's say, it'll produce a magnetic field. Okay, and in physics we use the symbol B, capital B, and an arrow on top. Arrow means direction. Okay, it's got a direction. And this happens, okay, and this magnetic field in turn can create an electric field. Okay, an electric field can create a magnetic field. This is all mathematical, and this is also provable in practice in the lab. This happens at the speed of light. C is the speed of light. It's a number. Okay. It's Latin for, I can't pronounce it, celeritas. I think that's how you pronounce it. It just means swift. Okay, it's the speed of light. So that's what light is. It's basically electric and magnetic fields changing into one another. Okay, ad infinitum. Ad infinitum. Okay, so this is what light is. So if I draw a set of axes, let me draw a set of x and y axes. Let's suppose I'm going to choose this direction to be up and down for the electric field. Okay, electric field looks like this. It's got arrows. So the arrows indicate, so in real life, this is not what it looks like, obviously. It's just a graphical representation. The arrows tell you the direction of motion. So it's moving up and down in this case. Okay, E for electric field with an arrow on top. I'll use a different color for the magnetic field. Magnetic field is going back and forth. Like so. I should say, sorry, there's another axis, the z-axis coming out of the page. That's right. Okay, B, magnetic field. Okay, this wave is moving at the speed of light, C. So that was the great breakthrough of 1865. Okay, there was a physicist before James Clerk Maxwell who actually believed that the speed of light, that light was an electromagnetic wave. Okay, it's made of electric and magnetic fields. That's what light is. So Faraday believed that, but he didn't have the mathematical proof to back up his argument. Okay, which is what you need in physics. You need a solid mathematical theory. So that's what light is. It's electromagnetic wave. Now, following Maxwell's discovery, well, they're all brilliant, these guys, the amazing work that they've done. If I go back up here. A German physicist named Heinrich, I don't know how to pronounce it, Heinrich Hertz, in the late 1880s, okay, so over 20 years, almost 20 years later, he proved experimentally the existence of what are called radio waves. Okay, he basically used a spark gap, attached to a special type of coil and a separate spark gap on a receiving antenna. So we had let's draw it briefly, had a transmitter and a receiver, which is how radios work. So a signal is able to move between the transmitter and receiver. Okay, so and they did so by sparks created, okay, in the coil. Okay, and what he found was that those waves were radio waves, okay, waves at a particular frequency. And then years after that, there were many other discoveries of different types of waves. X-rays, for example, came about roughly in the year 1895 by a physicist named Wilhelm, another German, Wilhelm, can't pronounce his name, I believe it's Röntgen. Okay, he discovered X-rays. And then you've got other types, gamma rays, okay, gamma rays, which are produced in things like nuclear reactions in stars as well, from exploding stars in space. You've got ultraviolet. Okay, so a lot of these different types of waves started popping up in experiments: ultraviolet, infrared, aka heat, microwaves, ... And then physicists come up with a way to categorize these waves. It turns out that all these different types of waves, all these different types of radiation, I should say, they're all the same thing. The only difference is their energies. Okay, these are all different types of electromagnetic radiation. So ultraviolet radiation, microwaves, they're the same thing. Okay, they're electromagnetic waves. They're basically electric fields becoming magnetic fields, becoming electric fields, ... And so physicists, scientists come up with a chart, a spectrum, called the electromagnetic spectrum. It looks something like this, roughly. Okay. You've got radio waves, followed by microwaves, followed by infrared, aka heat, followed by visible light, followed by ultraviolet, UV, followed by X-rays, followed by gamma rays. Okay, and that's it. That's the electromagnetic spectrum, EMS. From left to right in this diagram, you have increasing energy. Why is that? Well, suppose I've got a hypothetical box and I could fit, and I could see visibly, let's say hypothetically with my eyes, I have these superpowers, I can see peaks of a wave. Let's suppose I've got a wave that looks like this in the box, and a wave, and another box versus this box. Just 2 peaks. Let's say this one's got 4 peaks, I should say. 1, 2, 3, 4 versus 2 peaks. This box here with the waves inside, the electromagnetic waves, the waves are higher energy. Why are they high energy? Because they've got more peaks. Okay, this wave most likely will cause more damage to me than, let's say, the wave on the right, where there's just 2 peaks, less energy. Okay, so it's basically a measure of how many peaks you can cram into a space. This is why UV, ultraviolet radiation, causes skin cancer as opposed to microwaves, because there's more peaks. Okay, increasing energy, aka decreasing wavelength. Okay, wavelength is the distance between 2 peaks on a wave. Okay, 2 crests, 2 crests or 2 troughs as well. Whenever you make it shorter, so as you make the wavelength shorter, the more energy you've got, the more peaks, the more stuff, more energy. And also you've got increasing frequency as well, okay? So frequency is a measure of how many peaks, how many crests pass through a point per second. So these waves here have a higher frequency than these waves here. Okay, which is why we use radio waves and microwaves for communications for our mobile phones, let's say. And that's the electromagnetic spectrum in a nutshell.